Chapter 2, Binary Arithmetic. In any number system, when carrying out arithmetic operations, you have to follow a set of rules. And when adding two single-bit binary numbers, this is the binary addition rules that you must follow. The rules for binary numbers are quite straightforward and similar to those used in decimal arithmetic. The rules for addition of binary numbers are: when you have two binary numbers, 0 plus 0 adds to 0. When you have two binary numbers, when you add 1 to 0, the result is 1. If you add 0 to 1, the result is 1. And if you add 1 to 1, the result is 0, but you must carry a 1. So in binary addition, when adding two n-bit binary numbers, the binary addition rules are: add the individual bits, propagate the carries to the next highest significant digit. Pretty simple. So let's look at an example. Here we have the binary number 10101, adding it to 110011, which happens to be 21 and 25 in the decimal system. If you add, starting from the least significant digit, which is the immediate right, 1 plus 1 is equal to 0, and you carry the 1. 0 plus 0 is 0, but you're carrying 1, so the answer is 1. The third from the right is 1 plus 0 is 1. The next digit higher is 0 plus 1 is 1. The next digit is 1 plus 1 is 0, but you carry 1, and 1 is now in the next significant column. So you end up with a number 101110, which happens to be 46, and it is the decimal equivalent of adding 21 plus 25. So it all works. So looking at another example, we can say that binary addition is carried out much like we carry out addition with a decimal number, by adding up the columns starting at the right and working column by column towards the left. Just as in decimal addition, it is sometimes necessary to carry, and the carry is added to the next column. So if you were going to add a binary number 2, which is 10, to a binary number 1, which is 01, you'd end up with 3. 0 plus 1 is 1. 1 plus 0 is 0. The answer is 1, 1, which is equal to 3. So this example works. Okay, so let's do a little bit more complex of an example. By adding two 4-bit binary numbers, you're going to add the number 0, 1, 1, 1 to the number 1, 0, 1, 0. Starting from the least significant digit, the right-hand side, 0 plus 1 is 0. Moving to the next significant digit, we have 1, 1. So 1 plus 1 is 0, but we must remember to carry the 1. And we just put it up on top there to keep track of it. So the next significant digit is 1 plus 0 plus 1 is the same as 1 plus 1, which is 0, carry 1. And we put the carry up on top. So now we're left with 1 plus 1 plus 0. So it's 1 plus 1 is another 0, but you carry 1. So the answer is 1, 0, 0, 0, 1. So if we are going to check this out, we can check it out with a decimal equivalent. So the number 1010 is the number 10 in decimal. The number 0111 is the number 7 in a decimal equivalent. You add those together and you get 17. And if you look at our chart, 17 was 1, 0, 0, 0, 1. So again, the rules work. Let's move on to binary subtraction. There are 4 subtraction combinations possible when dealing with 2 single binary digits. Rules number 1, 2, and 3 are straightforward and are the same as if you were dealing with 2 decimal numbers. Rule number 1, 0 minus 0 is 0. Rule number 2, 1 minus 1 is 0. And rule number 3, 1 minus 0 is 1. Rule number 4, 0 minus 1 is 1. Now that needs a little bit of explanation because normally we cannot subtract something from nothing. It is similar to subtracting 1 from 1, 0. In order to subtract 1 from 0, you must first borrow a 1 from the next most significant digits. What we see here is only the end result of the borrow process. Another way of looking at it is subtracting a binary number 1 from the binary number 1, 0. But because we are only dealing with a single digit, we are only able to see the 0. However, we must remember that we borrowed the 1 from the next most significant digit column. So we can check this out with decimal numbers. If we take 1, 0 and replace it with a decimal number, that's the decimal number 2. 1, of course, equates to the decimal number 1. So you take 1 from 2 and you're left with 1, of course, in the decimal system. In the case of the binary system, 1, 0 minus 1 is 1. So again, the rules work. When subtracting multi-digit numbers, it helps to consider them in terms of their base and weight values. If a 1 appears in the least significant position, the decimal equivalent is 1 times 2 to the 0 power, which is equal to 1. If a 1 appears in the next significant position, the decimal equivalent is 1 times 2 to the first power, which is 2. If a 1 appears in the next significant position, the decimal equivalent is 1 times 2 to the second power, or 2 squared, which is 4. And if a 1 appears in the next significant position, the decimal equivalent is 1 times 2 to the third power, or 2 cubed, which is 8. Now, if we borrow an 8 from the most significant bit register, it is equal to 2 4s in the next significant bit register, or 2 binary 1s in that register. If we borrow a 4 from that register, it is equal to 2 2s in the next significant bit register, or 2 1s in that register. Lastly, if we borrow a 2 from that register, it is equal to 2 1s in the next significant bit register, which is equivalent to 2 binary 1s in that register. So keeping that in mind when subtracting, we subtract from right to left, so we begin with the least significant column. This means when we subtract 1 from 0, we cannot subtract 1 from nothing, so we must borrow a 1 from the next significant column on the left. However, the next column occupies the 2 place, and it actually consists of 2 1s. So we now have a column. If we borrow 1 from the next significant number, We have 2 ones that we've borrowed in the least significant digits, so we actually have 3 ones there. So now if we subtract 1 from the 3, we're left with 1. As we move to the left, we see that after borrowing 1, we are left with subtracting 0 from 0, which is 0, and the process is finished. No matter the place value, whenever we borrow from the next significant column containing a 1 in binary, we always borrow a 2, a 1, 0, and splitting the 2 into 2 1s. From the borrow operation, we always record 2 additional 1s in the needed column. Let's check this out with a decimal equivalent. Converting the top number 10 to a decimal number gives us the number 2. And converting the bottom number 01, which we're subtracting, that gives us the number 1, which checks out because 2 minus 1 is 1, and that's what we are left with in the binary operation. Let's walk through another example. Calculating the least significant column yields us a 1. There is nothing left in the next column, so that yields us a 0. Calculating the next significant column takes us through a borrow concept and yields 1. And there is nothing left in the next column, so that also leaves us with a 0. Going through the checking process using decimal equivalents, converting 10, 10, it comes to 10, and converting 01, 01, that gives us the decimal equivalent 5, and 5 from 10 gives us 5, and the 1, 0, 1 in the binary arithmetic yields us a 5, so it checks out. So I'm not going to take a long time to go through this, so just let's quickly go through the process very fast. We can see here that going through the processes of borrowing and subtracting, we're left with 0, 0, 1, 1. And when we check that against our decimal equivalent, 1, 0, 0, 0 is 8, 0, 1, 0, 1 is 5, so 5 from 8 leaves 3. And 1, 1 checks out to be 3. So again, our process checks out. The multiplication rules for 2 single-bit binary values are much the same as what they are with decimal numbers. If you have 2 numbers, the A column and the B column, A being 0, B being 0, you take 0 times 0, you're left with 0. In the A column, you have 0, B column, you have 1, so 0 times 1 is 0. In the A column, if it's 1 and the B column is 0, you have 1 times 0, it's still 0. If you have a 1 and a 1, 1 in the A column, 1 in the B column, 1 times 1 is equal to 1. No big surprise there. Let's go through the calculation of multiplying 2 4-bit numbers together and see what the answer is. The 2 4-bit numbers are 1110 times 1011. And we approach this much in the same manner as we do with a digital multiplication. start with the least significant bit and you follow the rules. 1 times 0 is 0. 1 times 1 is 1. 1 times 1 is 1. 1 times 1 is 1. So the number is 1110. Now, when we multiply with the next significant number, we have to shift everything over because we're in the next significant bit, but the rules still hold. 1 times 0 is 0. 1 times 1 is 1. 1 times 1 is 1. 1 times 1 is 1. So now we have 1110. The next significant bit is a 0. So when we multiply any number by 0, we come up with a 0. We have to shift one register to the left because it's now the third most significant digit, but they're all zeros. Going for the last significant bit, we still multiply using the same rules, and no big surprise, we end up with a number 1110, but everything is shifted one value to the left. Now, we add up all of those columns together, and we get 0, 1, and we get a 1 and a 1, which gives us a 0 to carry 1. So you get a 1 and a 1 plus a carry 1 is 1, and a 1 and a 1 with a carry 1 is 1 to carry 1, and 1 and 0 is plus a carry is 0, carry 1. 1 and 1 is with a carry is 0, and you have a carry of 1. You follow that? We were just adding up the columns vertically. Whenever we get a 0 in the column, of course it's 0. Whenever we get 3 1s, we have to carry 1 forward to the next column. So the answer is 1 0 0 1 1 0 1 0. So what does that convert to in decimal numbers? Well, we can do it by using the power of the weight value. So we're going to have nothing for the first number because it's 0. The second number is 2 to the first power. The second number, 2 to the second power, is a 0, so that doesn't show up as significant. The next significant one is 2 to the third power. The next significant one is 2 to the fourth power. Then we have the fifth and the sixth power are 0, so we don't have to calculate those. But the last number is 2 to the seventh power. Now, if you multiply those powers out, add them together, you get 128 plus 16 plus 8 plus 2 is equal to 154. The numbers that we started with, 1110 is 14, 1011 is 11, and you multiply 14 times 11, and you come up with 154. So no big surprise that our theory of our rules for multiplication check out. This ends Chapter 2.